Okay, so next question we ask is, what's the manner in which heat manages to flow? We say you got these calories. I mean, how does it flow? What's the rate? What makes it flow? So it turns out there are three popular ways of heat transfer. One is called radiation. Radiation is when the heat energy leaves some hot body and comes to you without the benefit of any medium, like heat from the sun. So that's really electromagnetic radiation that comes from hot glowing objects and directly comes to you. And electromagnetic radiation doesn't need air, doesn't need anything. And the second way of heat transfer is called convection. So convection is explained by this following example. You got water, you put it on a hot plate. Then in the lower part of it, the water gets hot. When it gets hot, it expands. And when it expands, the density goes down. Therefore, by loss of buoyancy, it will start rising up. Remember, a chunk of water belongs in water. A chunk of something else with lower density will float to the top. But the point is, water doesn't have a fixed density. If you heat it up, the density goes down. So the water guys downstairs have a lower density. They're like a piece of cork. They will rise to the top. When they rise to the top, the cold water with a higher density will fall down. So you will set up a current. Hot rises to the top and cold comes down. And this also happens in the atmosphere. On a hot day, the air next to the ground gets really heated up and it rises and the cold air comes down and you set up these thermal currents. So here you're trying to equalize the temperature between a region which is cold and a region which is hot by the actual motion of some material. In radiation, you don't have the medium transferring heat because the medium is not even present in radiation. In convection, the medium actually moves. The hot guys physically move to the other place and the cold guys come here, and by that process, the heat is transferred. The heat transfer I want to focus on is a little more quantitatively is conduction. So heat conduction is something you've all experienced. I mean, if you have a skillet, why does it have a wooden handle? The simple reason, if you had a steel handle, you put it on the hot stove and you put your hand here, the fact that your body is at whatever 98 degrees and this one is God knows 200 degrees, you're going to have heat flow from here to here. So we want to understand what's the rate at which heat flows from hot end to the cold end. So you can imagine a rod of some cross section A. One end of the rod is in some reservoir at some temperature T1, other end is at temperature T2. By the way, I'm now introducing a new term called reservoir. Reservoir is another body like you and me, except it's not like you and me. It's enormous. It is so big that its temperature cannot be changed. You can sit on it, you will fry and you'll evaporate, but its temperature will not change. No body is really a reservoir. If you drop an ice cube in the Atlantic, you lower the temperature of the Atlantic, but by a negligible amount. So take the limit of Atlantic goes to infinity, then you have a reservoir. This is connected on the left to an enormous tank of maybe a water-ice mixture at 0 degrees. This is a water-steam mixture maybe at 100 degrees. You put a rod there, we know heat is going to flow from the hot body, from the hot end to the cold end. And we want to write a formula for how much heat flows per second. Again, I'm going to write these formulas over and over again. So you've got to ask yourself, what will it depend on? What are the properties it will depend on in general, independent of what the rod is made of? Okay, let me repeat this argument. You take one rod, for convenience, let's just take it to be a rectangular rod. Take another rod, rectangular rod. They will both transfer the same amount of heat per given amount of time. Just glue them together and say, here is my new rod. We know it's going to transmit twice the amount of heat. So it's going to be proportional to the area. And why is the heat flowing? It's flowing because of a temperature difference. So that's always there. That's the underlying force for heat transfer. That's the dynamics and thermodynamics. That's what makes the heat flow. But then we find as an empirical fact that if these two reservoirs were separated by that distance, then the heat flow is a lot less than when they're closer. it seems to depend on how much temperature difference is packed in spatially. So you want to divide by delta x is not infinitesimal. It's the length of the rod separating the hot and cold ends. In other words, if you dilute the temperature difference over 1 mile, the heat flow will be correspondingly reduced. Whereas if there's huge temperature difference between a very small spatial separation, there'll be very robust flow of heat. That's what we're saying. These happen to be true, you realize, independent of what material I'm talking about. When I said 1 rod plus 1 rod is 2 rods, it doesn't matter what it's made of. Again, having put all these factors, which you can argue on general grounds, you have to now ask, what happens when this is a copper rod versus a silver rod versus a wooden rod? So you've got to put one more number, which is kappa here, not K, you guys. It's kappa, and it's called the thermal conductivity of that material. Sometimes you put a minus sign. Minus sign just means it flows from hot to cold. I don't care whether you put the plus sign or don't put the minus sign. Anybody knows that the heat is going to flow from hot to cold. So just remember that direction of flow, and that's all I care about, this sign here. This kappa is a property of the material. In the old days, people just said it's a fluid, and they postulated the conservation law for the fluid. You can postulate what you want. You got to make sure it works, and it seems to work in the sense that all the delta Q's in any reaction add up to 0. But then people were getting hints that maybe this thing that we call heat is not entirely independent of other things we have learned. So where do you get the clue? One clue is long back when we studied mechanics. We talk about 2 cars. They come and collide. They slam into one big lump. Now you've got no kinetic energy, no potential energy. Potential energy is always 0. They're moving on the same height. Kinetic energy was 1/2 mv squared for this, 1/2 mv squared for that. At the end, there's nothing. No kinetic, no potential. We just gave up and said, look, conservation of energy doesn't apply to this problem. We just say it's inelastic. On the other hand, we find whenever that happens, we find the bodies become hot. So you find very often mechanical energy is lost and things heat up. So you get a suspicion, whatever the underlying mechanism, maybe there is a rule that says if you lose so much mechanical energy that you cannot account for, then it translates into a fixed number of calories. If that is the case, then we'll at least get a dictionary on between calories and joules. So joules is energy you can see. Calories is energy you cannot see. That was going to be the premise. But first you got to prove that every time you lose some number of joules, you get a fixed amount of calories. And that experiment is due to Joule. Here is a Joule experiment. It's very, very simple and tells you the whole story. You have a little container in which there is a paddle. This is a shaft with a pulley, and there is a weight here. So look, I try to imagine this, guys. You got rope wrapped around the top pulley, and when you let this weight go down, it's going to go down like this. It's going to spin the shaft. I put some water here, and I have some fins that are sticking out, so that it'll churn up the water. What he did was to put these paddles, let the weight go down from there to here. Now we can keep track of how much mechanical energy is lost, right? Because if this mass was at rest, and it dropped the height mg, dropped the height h, it's supposed to have mgh kinetic energy. Let's say it's got some kinetic energy, which is not equal to mgh. So mgh minus kinetic energy is missing. So some number of joules are gone. But the water gets hot. When the water gets hot, you can immediately ask how many calories was supplied to the water, because that water heats up the same way whether or not you put it on a hot plate or whether or not you churn it. It doesn't seem to depend on how it got hot. This has the same effect. This water is hot in every real sense. So you must have put some calories. So you can find out how many calories you put in by looking at the mass of the water. Specific heat of water is 1, looking at the increase in temperature. So some joules are missing. Some calories have been pumped into the water. then you ask, is there a proportionality between joules and the calories? And you find there is. And that happens to be 4.2 joules per calorie. In other words, if you can expend 4.2 joules of mechanical energy, you got yourself 1 calorie to be used for whatever heating purposes. So in the example of the colliding cars, this had some energy, that is some energy, all measured in joules. They slam together, they come to rest. That means you can take those many joules, divide by 4.2, and get some number of calories. Imagine the whole car is made out of copper. Then those calories will produce an increase in temperature, right, equal to delta Q is mc delta T. That will be the rise in temperature of the car. In practice, there will be other losses because you heard the sound. Well, that's some energy gone. You won't get it back. Maybe sparks are flying. That's light energy that's gone. If you subtract all that out, you find that in the end, the calories explain the missing joules. So that made people think that this is just another form of energy. But the question is, what right do you have to call it energy? Energy, we think, primarily, when you say somebody's energetic, you mean that someone's running around mindlessly back and forth. Right? Energy is associated with motion. These two cars were moving, and we have every right to say they have energy. How about potential energy? Well, if this car starts climbing up a hill and slows down, we think it's got potential. You let it go, it'll come back and give you the kinetic energy. So most people's idea of energy is just kinetic energy. That is lost. And yet you get calories in return, so you ask yourself, what can it be? Well, the correct answer to that came only when we understood that everything is made up of atoms. Once you grant that everything is made up of atoms, then it turns out that kinetic energy of atoms is what we call heat. But you've got to be very careful. Take a tank full of gas. I throw it at you. That whole tank is moving. That's not what I call heat. Okay? That motion you can see. I'm talking about a tank of gas that doesn't seem to be going anywhere. Yet it got motional energy because the little guys are going back and forth. So what we will find, this is what I'm going to show you next time, is that if you kept track of the kinetic energy of every single molecule in this car, every single molecule in that car, before and after, and you added them up, you will get exactly the same number. The only difference will be, originally the car has got global common velocity, macroscopic velocity you can see. On top of it, it's got random motion of the molecules that make up the car. So does the other car. When they slam together, the macroscopic motion is completely gone, and all the motion is thermal motion. But it's still kinetic energy, and that's what we will see the next time.